Okay, let's unpack this. We often think that training in AI to truly reason, to solve complex problems like a skilled mathematician requires these incredibly intricate, cutting-edge techniques.
Right, especially in the world of advanced reinforcement learning, there's definitely a lot of focus there.
But what if a surprisingly simple approach wasn't just keeping up, but maybe sometimes even outperforming the complex stuff?
That's kind of the buzz right now. Yeah.
And that's the big takeaway for you, the listener, right? That you don't always need these incredibly complex algorithms to get, well, impressive results.
And what's fascinating here is this real push to get large language models to do more than just, generate text.
Exactly.
Models like OpenAI's O1 and DeepSeek R1 have sparked huge interest in their potential for complex reasoning, particularly in math.
Right, math is a big one.
And as we've seen, reinforcement learning, with methods like proximal policy optimization, PPO as it's usually called, has become a really popular way to fine-tune these models for those challenging tasks.
Exactly. And for this deep dive, actually, a brilliant listener like yourself sent in a fantastic collection of research.
Oh, cool.
Yeah. And one paper in particular really made us stop and think. It challenges the idea that we always need these super complex RL algorithms to get the best LLM reasoning. It's like asking, do you need a Formula One car to drive to the grocery store? Or, can a well-tuned sedan do the job just as effectively?
And maybe be easier to handle, too.
Right. Maybe easier.
So this raises a really important question. Is all that intricate RL machinery truly essential?
Yeah, is it overkill sometimes?
Or could simpler methods be just as effective, maybe even revealing some fundamental insights we've been missing?
Right.
The paper we're diving into today, a minimalist approach to LLM reasoning, from rejection sampling to reinforce, tackles this head-on.
Okay, so our mission today is to break down the findings of this research. We're going to explore the core ideas, try to cut through the technical jargon,
Yeah, make it make sense.
and really understand why these simpler techniques, like something called rejection sampling, and the crucial aspect of how we select our training data can be so surprisingly powerful. We'll even look at a method called RAFT, which honestly sounds incredibly basic on the surface,
It does.
and see how it measures up against these complex algorithms like GRPO and PPO.
Right.
So let's get into the details.
Okay, let's start with RAFT. That stands for rejection sampling fine-tuning.
Right.
And as the name suggests, it's a surprisingly direct way to apply reinforcement learning to LLMs.
Straightforward is almost an understatement, maybe.
Yay!
Okay, so how does this RAFT thing actually work?
So at its core, RAFT has three main steps. First, for each problem or prompt you give the LLM, you have it generate multiple different answers the paper mentions and responses per prompt. In their experiments, they often used 4.
Okay, so it's like the AI is doing its own little brainstorming session, coming up with a few different ways to tackle the problem. What happens next?
The second step is evaluation. For each of those generated responses, you use a reward function to score them.
Okay.
And in this paper, they used a very simple binary reward. If the answer is correct, it gets a reward of 1. If it's incorrect, it gets -1.
So super simple, just a basic thumbs up or thumbs down for each try.
Exactly. Correct or incorrect.
Got it. The AI tries a few times. We see which attempts actually hit the mark, and then what's the final step?
The final step is the fine-tuning itself. RFT keeps only the responses that receive the highest reward. So in this case, just the correct answers.
Only the winners.
Yep. Then it retrains the LLM specifically on this collection of positive, correct examples.
That's it. Just train on the good stuff and ignore the bad. It feels, I don't know, almost too simple.
Well, yeah. But as we're already learning, simple can be powerful.
It's true.
Its simplicity is actually one of its key strengths. It makes it very easy to understand and see what's happening under the hood.
Okay.
The researchers also briefly mentioned an earlier method called STAR, which stands for self-taught reasoner.
Ah, STAR. Heard of that one.
Yeah, and while STAR also trains on reasoning steps it generates itself, there are some key differences.
Like what?
Well, STAR basically restarts the training process from the original pre-trained model in each iteration, rather than continuously updating the current model like RAFT does.
Okay, so it keeps going back to the beginning.
Right. And it also typically generates only one response at a time, unlike RAFT's multiple attempts. Plus, sometimes it adds the correct answer right into the prompt for harder problems.
Interesting. Good to see how these different approaches kind of build on each other or diverge.
Definitely.
So RST is this straightforward filter. Generate multiple answers, judge them, keep the best ones, and learn from those winners. Now, you mentioned it's a reinforcement learning algorithm. How does it relate to the more, let's say, traditional policy gradient methods we often hear about?
Good question. Let's talk about policy gradient and a foundational algorithm called Reinforce.
Okay.
The basic idea of policy gradient is to directly tweak the LLM's policy, its internal strategy for generating text, so that it becomes more likely to produce responses that lead to high rewards. Reinforce is a relatively, well, direct way of doing this.
Oh, so
Think of it like guiding the AI when it takes an action, like generating a specific word or token.
right. Each word is an action.
That eventually leads to a good outcome, like a correct final answer. Reinforce encourages it to take similar actions in the future.
Okay. So it's kind of like training a dog, maybe.
Hmm.
Reward the good behavior, and the dog will probably do it again.
That's a pretty good analogy, yeah.
You're not necessarily punishing the bad behavior directly,
Yeah.
just not reinforcing it.
Exactly. Now, Reinforce often uses a technique called importance sampling. This helps make the training process more efficient by allowing it to reuse past experiences.
Okay, makes sense.
And it also sometimes uses something called clipping. This prevents the AI's strategy, its policy, from changing too drastically in one go, which can sometimes mess things up, cause instability.
Right, keep the changes manageable.
Yeah. And just to reiterate, in LLMs, each word, or more accurately, token, that the model generates can be thought of as one action in this whole sequence of decisions leading to the final answer.
Got it. Okay, so Reinforce is a bit more involved than RAFT, but still a pretty fundamental approach. Now let's bring in another acronym, GRPO.
Yes, GRPO.
The paper highlights that it's been very successful, particularly with models like DeepSeek R1 when it comes to tackling math reasoning. What makes GRPO different?
Okay, GRPO, its full name, isn't really the key thing here. It's how it works. It uses a loss function that's similar to Reinforce, but with a crucial difference.
Which is
It replaces the simple reward with what's called a normalized advantage function.
normalized advantage. Okay, what does that mean?
Well, like RAFT, it also generates multiple responses for each prompt.
Right.
But instead of just a raw correct or incorrect score, it looks at how much better or worse a particular response was compared to the other responses generated for that same problem.
So it's relative.
Exactly. It does this by taking the reward, subtracting the average reward of all the responses for that prompt, and then dividing by the standard deviation of those rewards.
Okay, hang on. So it's not just about getting the answer right or wrong, but about how much better or worse you did compared to your own other EMs on that exact same problem.
Precisely.
That sounds like it could give a much more nuanced signal for learning, like grading on a curve. But the curve is just based on the AI's own efforts on that specific question.
That's a great way to put it. And here's a really crucial difference from RAFT.
Okay.
GRPO uses both the responses that were relatively good and the ones that were relatively bad during training.
Okay. Unlike RAFT.
Right. It learns from both what worked well within the context of that specific prompt and what didn't. This is a direct contrast to RAFT, which, remember, only trains on the positively rewarded examples, the correct ones.
Okay, so just to recap, we have RAFT simple, trains only on positive examples. We have Reinforce, a basic policy gradient method. And then GRPO, a more sophisticated version that uses these relative advantages and learns from both the better and worse attempts within a prompt.
That's the setup.
Given all that, you'd naturally assume GRPO would be the top performer,
Right.
or at least significantly better than simple RAFT.
And that's where it gets really interesting.
Yeah.
Research has discovered that RFT, this seemingly basic rejection sampling method that only trains on correct answers, performs surprisingly well.
How well?
In many cases, it achieved performance that was competitive with and sometimes even exceeded these more complex RL methods like iterative DPO.
DPO, yeah. Direct preference optimization.
Right. And it even got very close to the accuracy levels of PPO on those really challenging math reasoning benchmarks.
Which ones?
Things like Math 500, Minerva Math, and the Olympiad bench. Really tough stuff.
Wait a minute. So this incredibly simple method, just focusing on the correct answers, is hanging in there with the big leagues.
Pretty much, yeah.
That really goes against what you might intuitively think. I mean, we're always told that learning from our mistakes is absolutely key.
Exactly. And the paper emphasizes this unexpected finding. They showed results using different models, too, like Quen 2.5 Math 7b base and Lamame 3.23b instruct.
Okay, so not just a one-off with a specific model.
Right. It shows that RAFT's strong performance isn't just some fluke. This really makes you reconsider the common belief that negative feedback is essential for effective RL training.
This is fascinating. Okay, so if RAFT, which only uses positive examples, can be so effective, what does that tell us about the role of those negative samples that methods like GRPO rely on? Are they not as important as we thought?
Well, this was a major focus for the researchers. They found that the performance difference between RAFT-like methods using only positive samples and those that use negative samples was surprisingly small.
Really? Small gap.
Yeah. And in fact, RAFT often showed faster initial progress it learned quickly right off the bat.
Okay, quick learner.
But their deeper investigation revealed something even more important. Certain types of negative signals could actually hurt the model's ability to learn.
Heard it. Which ones?
Specifically, prompts where the LLM generated completely incorrect responses across all of its attempts.
Ah, okay. Where it just completely bombed the question every time it tried.
Exactly.
That kind of makes sense intuitively. If the AI is consistently way off base, maybe there's a fundamental misunderstanding of the problem itself.
Right.
And trying to learn from those totally wrong attempts could just confuse it, lead it down the wrong path entirely.
Precisely. And so to explore this further, the researchers developed an enhanced version of RFT called RAFT++.
Oh, RAFT++. Okay, adding some pluses. What's new?
This version incorporates important sampling and clipping techniques.
Ah, the things we talked about with Reinforce.
Exactly. It's essentially borrowing some of the stabilization tools from more advanced RL methods like PPO to improve upon the original simple RAFT.
So RAFT takes the core simple idea, and RAFT++ adds some of these stabilizing features from the more complex RL world. What were the results there? Did it help?
It did. RFT++ showed improvements over the original RFT. It led to faster learning overall and achieved even higher final accuracy.
Okay, better performance.
Yeah. And their experiments, where they sort of selectively removed different components of RFT++.
Like ablation studies.
Exactly, ablation studies. They showed that this clipping mechanism was particularly important for keeping the training process stable.
Especially when?
Especially when the model's behavior started to change significantly from its earlier behavior, clipping helped keep things on track.
Okay, so RAFT++ is even stronger,
Yeah.
getting closer to those top-performing methods. But the paper also mentions that its performance might eventually level off, or plateau. Why is that?
That's another really interesting finding. The researchers analyzed something called the policy entropy.
Entropy, okay, what's that measuring here?
You can think of it as a measure of how much the model is exploring different possibilities, how diverse its outputs are.
So high entropy means lots of exploration. Low entropy means it's kind of sticking to what it knows.
Pretty much. They also looked at Kale divergence, which tells us how much the model's strategy has changed from its starting point.
Okay. And what did they find with RAFT++?
They found that RAFT++A, because it only trains on positive examples.
Right. Still just the good stuff.
It experiences a rapid decline in policy entropy. It becomes less likely to try out different reasoning steps as training goes on.
Ah. So it gets good quickly by focusing only on what it knows works, but then it gets kind of stuck in a rut because it's not venturing out to explore potentially new, maybe even better solutions.
That's the idea. It becomes a bit rigid in its thinking.
Makes sense.
And this reduced exploration caused by the low entropy is what they believe leads to the eventual plateauing of RAFT++ performance.
I see.
And it helps explain why methods that do maintain more exploration, like GRPO, can eventually surpass it in the long run, even if RAFT++ started faster.
So there's a trade-off between exploiting known good solutions and exploring new ones.
Exactly. They even tried a technique they called clip higher, basically adjusting the cutting range to encourage a bit more exploration.
And did that help?
Yeah, they found that it helped RFT++ maintain better performance in the later stages of training, mitigating that plateau effect somewhat.
Fascinating. So RAFE highlights the power of simple positive reinforcement, but you still seem to need a certain level of exploration to keep pushing the boundaries. Okay, let's circle back to GRPO then.
Okay.
The paper suggested that its success wasn't just about that fancy reward normalization. What else did they find when they dug into GRPO?
Yeah, this was really insightful. They conducted a series of experiments looking at different variations of the basic reinforce algorithm.
What kinds of variation?
They tested vanilla reinforce, versions that subtracted the average reward like GRPO does, partly, and crucially, versions that selectively removed different kinds of training examples.
Removed examples. Which ones?
They tried removing prompts where all the generated answers were correct, prompts where all the answers were incorrect, or removing both types.
Okay, filtering the data based on whether the model aced the question or failed completely. And what were the key findings there?
The most significant improvement in performance came when they removed the training examples where all the generated responses were incorrect.
Ah, back to those completely flawed attempts. Getting rid of those helped the most.
By a significant margin, yes. This strongly suggests that these completely failed attempts were actually hindering the learning process.
Why, though? What's the theory?
Likely because they introduced too much noise or variance and potentially misleading gradient signals. Basically, trying to learn from total failure might just confuse the model more than help it.
Okay. And what about removing the other types?
Interestingly, just removing the examples where all the answers were correct didn't make much difference to the final performance.
So, removing the perfect scores didn't really move the needle much.
Not really, and perhaps most surprisingly, the reward normalization part of GRPO, subtracting the mean reward and dividing by the standard deviation.
Yeah, the bit that sounded sophisticated.
That, on its own, didn't seem to have a major impact on performance in their tests.
Wow. So it wasn't the complex reward calculation that was the secret sauce behind GRPO's success,
It seems not, or at least not primarily.
but maybe more about its inherent way of dealing with or implicitly downweighting these completely off-the-mark examples.
That's the key insight they landed on. GRPO, by evaluating performance relative to other attempts on the same prompt, likely just gives less weight to or effectively filters out these consistently bad prompts where everything went wrong.
Ah,
And inspired by this finding, the researchers propose a new, even simpler method.
simpler than GRPO.
Much simpler. They called it Reinforce-Rej.
Reinforce-Rej. Okay, Rej for reject, I assume. Tell me more.
Exactly. Reinforce-Rej is a very minimal extension of the basic policy gradient algorithm, Reinforce.
Minimal how?
Its main modification is that it filters out prompts that result in either all correct or all incorrect responses before doing the Reinforce update.
Wait, so it's not just getting rid of the totally wrong ones, like we just discussed, was beneficial,
Right.
but it also gets rid of the prompts where the model got everything right. Why would you want to filter out the perfect scores?
Yeah, that might seem counterintuitive at first. The thinking there is likely related to focusing the learning effort and being more efficient.
How so?
Well, if all the generated responses for a prompt are correct, the model has probably already mastered that type of problem, or at least that specific instance.
Okay, it doesn't need more practice on that one.
Right. Spending more training time on it might offer diminishing returns. It might not be the most effective use of computational resources.
So focus on the ones where it's still learning, where there's a mix of right and wrong, or at least some struggle.
Exactly. By filtering out the all correct prompts, along with the all incorrect ones, Reinforce-Rej directs the training towards the more challenging and informative examples, the ones where the model is still actively learning and refining its reasoning.
And how did this super simple Reinforce-Rej perform?
The impressive thing is that this very simple method achieved comparable performance to the much more complex GRPO.
Really? As good as GRPO?
Pretty much neck and neck, but Reinforce-Rej did it with better KL efficiency, meaning the policy didn't change as drastically and more stable policy entropy, meaning it maintained exploration better.
Wow. So a really lightweight and effective alternative just by filtering the training data in a smart way.
Exactly.
This is a real aha moment, isn't it?
Mm-hmm.
It feels like maybe we've been so focused on designing these incredibly complex, intricate algorithms
Yeah, the bells and whistles.
that perhaps we overlooked the fundamental importance of carefully selecting and filtering the data we use to train them.
Absolutely. The research strongly indicates that, at least for reward-based LLM post-training for reasoning tasks like math, the quality of the training examples, especially how we handle the negative ones, seems to be more critical than the intricate details of the algorithm itself.
Okay, listener, let's try to summarize the key insights we can take away from this deep dive into minimalist LLM reasoning. This was quite a journey.
Definitely. So, first, I'd say, surprisingly simple methods like RAFT, the one that only trains on positive examples, can be remarkably effective for getting LLMs to reason. They can often compete with much more complex approaches.
Right. Simple isn't always worse. What else?
Second, while training solely on those positive examples can lead to really rapid initial progress, it can also limit the model's ability to explore new solutions later on, that entropy collapse thing.
Okay, the exploration trade-off. Got it.
Third, and this feels really crucial, negative examples aren't always beneficial. In fact, prompts where the model gets everything wrong can actually hinder learning. They might be actively harmful.
Don't just learn from any mistake, maybe. Focus on the productive ones.
Something like that. Fourth, the success of algorithms like GRPO appears to be largely due to their ability to implicitly filter out or downweight these problematic, all incorrect examples, maybe more so than their fancy reward normalization techniques.
So the filtering is key.
It seems so. And finally, a very simple method like Reinforce-Rej, which just filters out prompts with all correct or all incorrect answers, can be a highly competitive and efficient alternative to more complex beasts like GRPO.
Yeah, that really underscores the aha moment for me, that simpler isn't always worse, and maybe focusing on the quality and selection of your training data is absolutely paramount.
It really shifts the focus, doesn't it?
It does. And it's also a bit of a release, right? It's just, for everyone trying to keep up, that we don't always need to chase the absolute latest, most complicated algorithm to make significant progress in AI.
Right. Sometimes a more thoughtful approach to the fundamentals like data curation can be incredibly powerful.
So, thinking beyond this paper, considering these findings, what other assumptions might we have about training advanced AI that could maybe be challenged by a more minimalist approach?
That's a great question. Perhaps in areas beyond mathematical reasoning, like creative writing or code generation, are there
Yeah.
parallels there?
Interesting thought. Could simplifying the training process yield surprising results elsewhere too?
Or maybe think about it this way. If simply discarding certain types of training data, the all wrong or even the all right examples can lead to such significant improvement,
Yeah.
what are the broader implications for how we curate and evaluate the vast data sets we use to train our most advanced AI models in general? Are we keeping data that might actually be holding them back?
That's a fantastic question to leave our listeners with. It really feels like this could be just the beginning of a fascinating shift in how we approach the development of these intelligent systems.
Definitely feels like fertile ground for more research. And for those of you who want to explore this specific work further, the researchers did make their code available online if you search for RLH flow and minimal RL.
Good to know the code is out there. It's a constantly evolving field for sure, and these minimalist approaches are definitely adding a new and frankly pretty intriguing perspective to the whole thing.